Hello everyone, my name is Erfan Arefin, and I will be presenting the paper Weaponizing IoT Sensors When Table Choice Poses a Security Vulnerability. The authors of this paper are Gustavo Casqueiro from the Military Institute of Engineering, Rio de Janeiro, Brazil, myself, Tasnia Ashrafi Heya, Abdul Serwadda, and Hassan Wasswa from the Texas Tech University, Lubbock, Texas. Internet of Things has been around for a decade and so. And the sensors involving the IoT paradigm is an integral part. In previous researchers have tried to infer user information in different attacks. In this research work, we tried to infer user information using IoT sensors. So the question that we focus on in this research is, can we weaponize IoT sensors? So we have used a motion sensor as our primary sensor in this attack. And the goal of this attack is to snoop pins or personal identification numbers from the keyboard. So we place the motion sensor under the keyboard. Technically, the keyboard is rigged. And it's possible due to the small size of the motion sensor. The thickness of this sensor is around 1.5 centimeter. We also investigate that. Now I'm going to talk about the threat scenario. We have two variants of the attack. The first one is where we place the sensors under the keyboard, and the second one is where we place the sensors under the table. And this is to spy on the victim's keyboard inputs. This can be considered as an insider job, so we assume that someone such as a colleague, office cleaners, roommates, or employers can place the sensors under the victim's keyboard or the table. The attack design is described here. On the left image, you can see that we have our attack victim. The motion sensors are placed under the keyboard of the victim. The victim types on the keyboard. The motion sensor picks up different sort of vibration from these keystrokes, and this data is transferred over Bluetooth to the attacker's computer. The attacker receives this data using the sensor software, and it extracts different sort of features from these keystrokes. Further, this data is fed to a pre-trained model to infer information about the pins that's been typed in by the victim. So for data collection, we have used a motion sensor from Weaponizing, and the model number is WT901BLECL. It is used to get motion information such as accelerometer, gyroscope, and angles. This sensor also provides magnetic field information, which we do not use in this research work. The data is transferred over Bluetooth to an Android device or a desktop machine. And these sensors are placed under the numeric pad as we are focusing on the pins. For our data collection, there were 23 participants involved for all the experiments. So we had a separate set of participants for training, and we had a separate set of participants for testing. So for training, the participants had to type 0 to 9 on the keyboard, each keys 3 times. For testing, we had used different pins of 4, 6, and 8-digit lengths, and the participants typed 5 pins of each length, a total of 15. We had used 4 different tables in our research. We had used plastic table surface, metallic table surface, glass table surface, and wooden table surface. So the data that we had received, we removed any row that had empty values, and we had used only the motion sensor data. We had ignored the magnetic sensor data. For feature extraction, we used the TS-Fresh library, and using that, we were able to extract 55 statistical and time series features. The evaluation is categorized into two parts. The first one is keystroke inference attack, and the second one is detecting keyboard movements. So for the keystroke inference attack, it is basically a 10-class problem, since we are trying to classify numbers from 0 to 9. And we had, on a separate experiment, we had used different table surfaces. So when we use when we placed the sensor under the keyboard, we had used 2 sensors. And when we had placed the sensors under the table, we had used 4 sensors. So the classifiers that we used are XGBoost, Light GBM, and a voting assemble. Now I'm going to talk about the classification result. So now I'm going to talk about the classification results. So we have 4 different classification results here. On the leftmost side, we have the results where we place the sensors directly under the keyboard. And the next 3 are the results where we place the sensors under the table surface. So we have used plastic, glass, and metallic table, and we had also used wooden table, but we have not included the results for the wooden table in our work, as the results were not good. Right, so now I'm going to talk about classification results. In this slide, I have 4 different images describing the accuracy of our attack. So on the leftmost image, I have the results for the experiment where the sensors were placed directly under the keyboard. And on the next 3 image, I have the result for 3 different table surfaces. So on the leftmost attack, we can see that we have S1, S2, S1 plus S2. So we have included the results for independent sensors too. So if we had used only sensor 1, how would the accuracy be? If we had used only sensor 2, and also we have the results for the combined sensors. And we have included the best performing standalone classifier, meaning the leftmost image and the next image has XGBoost, meaning the XGBoost classifier performed the best. And we also have results for voting assemble, where we had multiple different classifiers, and we used an assembler to enhance the accuracy. And on the leftmost image, we can see that we have a 93% accuracy when we used both of the sensors and when they were placed on the table. And on the next 3 image, we have the results for individual sensors. In this 3 experiments, we had 4 different sensors, so we have those results separately in this classification results. So for the glass table and the metallic table, the standalone classifier that performed the best is Light GBM. Next, I have the confusion matrix that was produced by voting assemble classifier when the sensors was under the keyboard. So we also did another study where we focused on the accuracy distance relation of the keys and also the average accuracy of each key classification based on the rows and the columns and their distances from the sensor's midpoint. As you can see that as far the keys goes from the sensors, row-wise, the accuracy decreases, and the accuracies are and the accuracies are higher as long as the columns are aligned with the sensors. For the keyboard movements, we have categorized this experiment into two parts: keyboard rotation and keyboard translation. For keyboard rotation, we have conducted the experiment in three different positions. So the initial position is when the keyboard is placed horizontally on the user's table, and then we rotate the keyboard to the left by 15 degrees. That's our R1 position. And then we rotate the keyboard to the right 15 degrees from the initial position, and we name that R2 position. For the translation, we have moved the keyboard to the upside, and we've marked that as T1. To the right, we have marked that as T2, and then from the initial position to the downward, we have marked that as T3, and again, to the left, we have marked that as T4. So we have total 5 positions. Now I'm going to talk about the impact of the keyboard movement on the collected data. So on the left, I have a 2D plot for keyboard rotation. On the x-axis, I have sum of recurring data points of AX. So this is the x-axis data from the accelerometer of the motion sensor. On the y-axis, I have the data for skewness of WY, which is in degrees per second. And this WY is the data of y-axis data of the gyroscope. And when we plot that, we can visually distinguish the 3 different positions, R0, R1, and R2. On the right side of this slide, we have the 2D plot for keyboard translation. In the x-axis, we have the mean of AX, which is the x-axis data for accelerometer. And on the y-axis, we have the mean of AY, which is the y-axis of the accelerometer data. And we can visually distinguish the 5 different positions, T0 through T4. So from this information, the attacker can detect whether the keyboard was moved, whether it was rotated, or whether it was moved in a translation manner. Based on that, he can take informed decision on his results of the inference attack. Thank you very much.